Fantastic. And welcome, everyone. Thank you so much for joining us today for this 15th BatteryMBA Roundtable. Everyone is coming in. I'm just going to give it maybe 30 seconds or so to make sure people can join here, of course, live in the cohort from the 15th BatteryMBA cohort, as well as online on LinkedIn, as well as on YouTube. So yeah, just going to give it a few more moments so all of you can join for quite an exciting roundtable. I have to say, personally, I've been doing quite a few of them over the years, but I'm very excited for today's conversation. Fantastic. And also just everyone here, if you're listening in from LinkedIn or YouTube, would love to hear where you're calling in from. So please, if you can put it maybe in the comments where you're calling from, would really, really love to see that. Always fascinating to see where you're all sitting. And of course, here in the cohort, wonderful to have you all here. The first part is public and with LinkedIn and YouTube. And then the second part is exclusive to this cohort. And yeah, very excited to have you all here. And with this, we might get started because I think people are coming in. Just a quick word as well. There's two LinkedIn events. One is with the live stream and one is with the registration form. So if you sign up for one of them, they should link with each other. But if you have any challenges, just put a comment on LinkedIn and we're going to help you out. Fantastic. Before we're going to go to this really, really exciting lineup today, we want to quickly just share a few quick words about who we are with BatteryMBA and the Battery Associates, so you know the organization behind. Want to keep it very brief, but let's go right into it. The first thing being Battery Associates here is really focused on supporting the battery ecosystem along 4 dimensions. You can see them here. Education, of course, this is where the BatteryMBA also sits, which we are today or this panel, a roundtable is part of. We're also very excited about innovation, developing innovative products in this regard, such as battery testing devices, and then also consulting, which is our trusted advisory arm, where we're helping large organizations and small organizations on their really exciting journeys in the battery space. So if you're a big automotive OEM or a startup, don't hesitate to reach out. And then also community, of course, very excited about bringing people together, facilitate collaboration, and we have an ambassadorship and also alumni and really fantastic experts all around the world, which are helping making all the other 3 parts of our organization work. And if you maybe go to the next slide, BatteryMBA, it's incredible how far it has come. Now we count more than 700 alumni, and I want to give over to Garima to give us some more information about the program.
Thank you, Simon, and welcome everyone. Thrilled to have you here, thrilled to have our speakers here. So very briefly about the BatteryMBA, for those who don't know, it is a 12-week live online program held 3 times a year and is specially designed for working professionals seeking practical industry-relevant battery knowledge. The program combines live lectures given by leading industry experts along with engaging discussions during office hours, a case study track, a mentorship program, and a few other sessions. And the curriculum covers typically the entire lithium-ion battery value chain. The program has consistently received excellent reviews, with 98% of participants saying that the BatteryMBA has met or exceeded their expectations. And our diverse community includes over 700 participants from 60 plus countries, representing leading organizations from across the battery ecosystem, from Tesla to ABB, Schneider Electric, Hitachi, and a lot more. And the program attracts a wide variety of profiles, making the peer exchange a very big and important part of the learning. And we quickly want to highlight that our next intake for the January cohort ends on the 29th of December. So we really love to have you join us. We're excited. If you're excited about accelerating your own career in the battery industry or to support others in your organization and network, please don't miss this chance. We also offer a range of partial scholarships aimed at supporting individuals from underrepresented backgrounds in the battery sector. And because building diverse and inclusive community is at the heart of what we do here at Battery Associates. And if you have any questions, we're here to help. Please reach out to us by email at info@battery.mba. And we're also happy to share that for a limited time only, we have a Black Friday offer. So if you enroll by the 30th of November with the code BMBF 2025, we offer free access to a future cohort's recordings, which includes about 10 lectures. And with that, I hand back to Simon.
Thank you so much, Karima. And yeah, I think one thing also which we absolutely love is to meet each other in person. Of course, the BatteryMBA is an online program which makes it very easy for people to participate from around the world, as Karima shared. But again, we also love to meet with other alumni at events. And we had a few here more recently in France and Spain and North America, as well as in the Middle East and in Europe. And actually right now, a couple of us are actually in Berlin for another event, the Future Battery Forum, which we're very excited for. So if you're here, please make sure you say hi at our booth. And we also have BatteryMBA and meetups there. It's definitely always a highlight to meet each other in person. It's something we always like to foster and support. Go to the next slide, please. And then, yeah, one more thing is also we have our battery day, our own battery day in 2026. We just had one in September. We have another one next September, which we're very, very excited for. It's a wonderful way to connect with each other from around the world. It's a 12-hour event we have been running for 5-6 years now. So the 7th edition is to come. And yeah, please save the date for the 24th of September, 2026. And if you're interested to become a speaker or sponsor, you can already let us know via the email we mentioned, info@battery.associates. And with this, we're going to go to what we are here for, which is the roundtable. So really appreciative that we were able to go through this in 5 minutes or so, because we got the feedback we should maximize our time for the roundtable. We couldn't agree more. So yeah, we have a wonderful lineup, as you can see on this slide. And let me maybe just kick it off with our first speaker of the day. Of course, we have Professor Dr. Stan Whittingham. We also have Dr. Asma Sharafi and Dr. Mara Kubik. But let me kick it off with Stan right away. And Stan, who was actually fortunate to meet not too long ago in the US at the Battery Show North America, which was wonderful to see you in person, Stan. And he's widely regarded as one of the founding figures of modern battery technology. His contributions earned him the 2019 Nobel Prize in Chemistry, recognizing decades of pioneering research that fundamentally reshaped the energy landscape. Today, he continues to lead scientific progress as Distinguished Professor and Director of Northeast Center for Chemical Energy Storage and Battery NY at Birmingham University, advancing materials research and energy storage innovation. Stan, absolute pleasure to have you with us today.
Thank you.
Thank you, Simon, and a big welcome to Professor Whittingham. Now it's my pleasure to welcome Dr. Asma Sharafi, who is a seasoned executive in battery and energy storage technology. She combines deep technical roots with leadership and innovation. Her early career included advanced work in lithium metal and solid-state battery systems, and she brings over a decade of experience moving breakthroughs from the lab to commercialization. And in her most recent role as CEO of PowerCo US, she has led efforts to scale next-generation battery technologies, aligning strategy, manufacturing, and product development at a global level. Thank you for joining us, Dr. Sharafi.
Thank you for the opportunity. Looking forward to it.
Fantastic. And last but not least, we have Dr. Mara Kubik with us, who is a prominent energy storage industry expert with 16 years of experience. He holds advisory roles with the board of Whittingham & Co. and the UN, and is leading efforts to enable the world's first 100% renewable power grid at scale in the Middle East. Prior to this, Dr. Kubik was a founding member of the energy storage technology leader Fluence, serving as the managing director and helping it grow from a startup to a 4.7 billion IPO and beyond. Dr. Kubik brings the perspective of a thought leader who straddles technology, business, and large-scale systems transformation. Marek, absolute pleasure to have you.
Thank you, Simon. Looking forward to it.
Fantastic. So we have a lot of questions, but of course, as if you know us, we also want to make sure the audience can ask their questions. So this is already an invitation for everyone on LinkedIn and YouTube, but of course also here, as this cohort is on Zoom as well. Please make sure to put your questions for our fantastic panelists in the chat so we can make sure we address them. We want to get to as many of your questions as possible. So a big, big invitation. Please make sure you put your questions in now. And my personal experience over the last years has been most questions come in the end, and then it's very difficult to go through them. So my big invitation would be, please put them in early so we have a chance to actually address the questions you have. But maybe I can start it off with Stan. And I would really like to understand a bit from your perspective, as you have seen this entire industry really coming to life for the past decades, and based really on your research and innovations you have been creating. And maybe if you could share a bit more about like, how has this vision you had, right, like quite a few years back, decades back, evolved, and could you have seen it evolving this way? And maybe also what has surprised you as the most, both in a positive but also maybe negative aspect on this trajectory?
Yes, thank you. Let me just pronounce the word Binghamton. Okay. No P in it, unlike the English and the other places. So I started in this area 50 odd years ago, and our goal at Exxon was to make batteries for electric vehicles. So here was an oil company seeing the vision for the future was more than just oil. So we built some prototypes, we sold a few batteries, but then the market wasn't really big enough for a company of Exxon's size. They wanted $100 million a year. So they sold that technology, and it was picked up by a number of companies, one in Asia, one in, I think, Germany, and one in the US. The real change came when Sony decided they were interested. They made all these gadgets, and they wanted to be vertically integrated. They wanted to make the batteries as well as everything else, and the batteries that time were not very good. So I think they licensed the technology from some other companies in Japan. Exxon did not license to Sony. It was somebody else, so they licensed from them. And the anode material from Bell Labs in the US. So there's a lot of activity there. And I think people should realize when I got in this business, there were really no computers, certainly no laptops, no iPhones. So the world was a very different place. And what our interest was really was to clean up the environment. Now, I was a student at Oxford, and when I went back to my home in Lincolnshire, I went through London. London was still burning coal at that time in homes. And you blew your nose, it came out black. So that was a goal of ours was really clean that up. And I think our goal and vision for the future is still in major cities, not necessarily in the countryside, we will go all electric. So all the vehicles will be electric of one sort or another. And we have a company in town here about 3 miles from my office, BAE Systems. They make hybrid buses, and they make the electrification system for the buses worldwide. And about half the buses in Binghamton are hybrid. So I think my real vision is we'll get more clean energy that needs batteries. And I think I'm very proud to say, unlike London back in the 60s, New York State does not make a single kilowatt hour of electricity from coal. And next step is we'd like to get rid of the heavy oil. So my vision is really a really clean environment with batteries really playing a role, and clearly their costs have to come down, their lifetime has to improve. But that's the real vision. Let's clean up the environment, make it more sustainable. And I hope Trump's colleagues aren't listening, but that should be our mission throughout the whole world.
I appreciate you sharing this vision. And also one thing I think you touched on is, right, like how it was a lot of different components which had to come together to make the first battery work, and lots of different innovation. Something we also strongly believe, right, and see here in the BatteryMBA, bringing all of these stakeholders together is essential to really make breakthroughs and a reality. Maybe one thing to add on this, Stan, I would love to hear a bit more about, because I mean, you have been really there from the intercalation cathode chemistry side, right? And really, now we see all of these other chemistries evolving, and maybe some less known ones, from lithium sulfur and sodium ion and semi-solid and solid state, etc. Maybe to get a bit of your perspective on that, maybe is there something you are most excited about right now, or like anything maybe even lesser known chemistries out there?
Well, I think if you look at all the chemistries you mentioned, they were all mentioned 30, 40 years ago. and things come around, lithium-ion has really been out there commercially successful commercially for at least 30 years now. So the prices have come down a long way. It'd be very difficult for any new technology to knock them off their perch. But to talk about a few of the areas, lithium sulfur we should be working on. It should be low cost. It's incredibly difficult from a technical point of view. People have been working on lithium sulfur since the early 1960s at General Motors, Argonne, amongst others. Sodium ion, a lot of interest, but a lot of companies have gone bankrupt in the last 6 months. And they've gone bankrupt because you cannot make an economic case for sodium ion batteries these days. Even if they're as good as sodium ion in safety and everything else, the energy density is half the amount. So the balance of cost of the system is twice as much, and people tend to forget about that. It's not just the active materials. But the real issue with sodium ion is people claim they're safe. The evidence lately, certainly with the layered oxides, they are extremely unsafe, less safe than lithium ion. So people need to be very careful working on sodium. Some of the phosphates look like they're good, and there should be some interest there, but they're going to be niche markets. Got to say, there's a cost issue there, even if most of the elements were free. Relative to solid state and semi-solid state, no. I was an advisor to QuantumScape for a while. I've been familiar with Blue Solutions, PEO, solid state, because that really came out of US Department of Energy, funding at 3M and Hydro-Quebec. That's commercial. It clearly has some issues because it has to operate at 60, 70 degrees centigrade. And it clearly is no safer than lithium ion. As anybody who saw the fires in Stuttgart on the buses or the two fires in Paris. So we have to be very careful on these new technologies, not to say they're safer until we know they're safer. And I have to remind everybody all the time, energy by definition is not safe. We control it. If it lets loose, we have problems. Semi-solid versus totally solid state. If you're talking totally solid state, we have issues at the interfaces. Now, I don't mean the interfaces necessarily between the electrolyte and the cathode. It's between the particles in the cathode, how the lithium ions or sodium ions jump from one particle to another. So typically today in the PEO, they mix the PEO with the cathode. QuantumScape adds a few drops of liquid. And if anybody tells you they have a fully solid state battery, ask them how many drops of liquid you add. And you'll find almost all of them add a little bit to the cathode to make that connection across those interfaces. So I think there's lots of opportunity out there. I think we talk a lot about chemistries. We don't talk enough about process. How do we make the materials? How do we make the cells? And so on. Those are now the critical issues, I think.
No, I fully agree. And I think this would have been another question exactly about the processes and for scale up, et cetera, we need. But I think you already touched on a bit, so maybe we can come back to this later. And now come to Asma, who of course spent quite a bit of time exactly on this topic, how to also scale up some of these technologies. But Stan, we'll come back to you. Thank you already so much.
Hi, Asma.
Hi.
Yeah. So we'd like to jump into the solid state question. Would you share your perspective on which chemistries you think we're going to see in the market, and how would they differ from lithium-ion batteries in terms of supply chain, cycle life, end of life?
Yeah, I think Stan had a good segue in introduction of the solid state. As we all know, solid state battery has three flavors: polymer base, oxide base, and sulfide base. Of course, polymer base is the more advanced one because it is the closest to the lithium-ion battery as a drop-in solution to use the infrastructure for battery manufacturing of the lithium-ion batteries. But there are drawbacks that, first of all, enabling the lithium metal can be a little tricky. It is mainly paired with graphite or silicon-based chemistries. But the safety advancement and the main goal for transitioning to solid state is the fact that you can enable the lithium metal batteries to push that energy density. That cannot be met by polymer base. The safety aspect is also going to be compromised, but that will be the first chemistry that we can see in the application. We are seeing an application, but yes, we cannot get the safety for granted just because this technology is known, and we have to test it in real application. Moving on, I think the oxide-based system is another one that has a high voltage stability. It can be paired with high nickel cathode chemistries, and it can really be the right match for the EV market just because you can achieve the high energy density. In theory, high energy density is a cycle life, the safety. All of that has to be proven in an application, not the cell level. The problem with the oxide-based system is the fact that they require a completely different material base and equipment in order to really get to the roll-to-roll processing. Defect densities will play a significant role in the reliability and scalability of this technology. It is holding promises, but do we have an application that is utilizing it on the roads if we are attaching into EV? I don't think we are there yet. And then on the sulfide-based system, I think that is the highest ionic conductivity. The main problem with them is the moisture sensitivity, the hydrogen disulfide that can be a problem related to the safety. But all of these materials have shown, and we have seen how from the lab, getting it to the scalability, each one of them are in a different stages. I totally agree with the Stan's point of view of semi-solid. We are categorizing, if you are using a solid state electrolyte, you're working on solid state, and there is a lot of announcement of solid state. But when you're digging deeper, you understand there is a semi-solid, you're adding that liquid electrolyte, and depending on how much electrolyte you're adding to the system, you are really compromising that safety. You are compromising the benefits of the solid state, that the failure modes can be related to the electrolyte and liquid electrolyte decomposition, as well as the interfaces between the solid electrolyte and the cathode materials itself. Related to the supply chain, of course, there is a shift that's going to happen. We are no longer needing the separator that acts as a barrier. That separator can be eliminated, replaced with with the solid state electrolyte that not only act as mechanical barrier, but also it can enable the lithium ion shuffling from anode to cathode. So there's going to be a shift from the salt and solvents, the carbonate-based solvent, into solid state electrolyte. Unfortunately, that is one of the other barriers of having that supply chain of the material for solid state electrolyte. We diversify, but at the same time, we need to work on making it much more the infrastructure in supporting that value chain. The other part will be related to the anode material. Again, we're transitioning from the graphite or silicon-based lithium metal. There are some technologies that do not even require having a lithium foil at the beginning. They mainly plate the lithium during their first charge and discharge cycle. And that means current collector will have a different flavor, and that is going to be the changes. Cathode, I would say it is very similar to what we have on the cathode that is being utilized in lithium-ion batteries, but a specific coatings that might be required. Related to the cycle life, again, we have seen cells in the labs. I call them hero cells that are achieving that thousands of cycle in a very controlled environment, apply the stack pressure, knowing what you're doing. But to see that thousands of cycle life in an application that is going through vibration in a module, that is something that we have to see, and we need to get to the point that we can really see, can we achieve that cycle life that is required if, again, we're attaching solid-state batteries to automotive. I don't feel necessarily we have to do that. We have to find out how we can get this technology in an application to see what is the field information coming, what are the failure modes, and really build that infrastructure that is needed around this specific technology. For the end of life, if you are talking about recycling, I would say we are removing that liquid electrolyte component. And liquid electrolyte component is known for that compromising the safety. Solid state, again, if we are talking about all solid state battery, that should be the goal if we get there. We can come up with a much more safe way of recycling because we're not having that safety issues. Well, if we are having sulfide, again, the exposure to moisture can be compromised, and then there's going to be problem, and we have to find out how we can do it in a controlled environment so we don't cause a hazardous gas being deployed. But I would say in the solid state, it is going to be a little different just because you're having different material. And as you're thinking about cell design and you want to really go after the recycling, maybe we have to consider what comes next for recycling and co-develop it, as a whole value chain, as a whole cycle, to know this material is going in, this is how it is getting connected to each other. And then if we can reduce and remove the amount of additives, the conductive items that will be used, we are transitioning to dry processing. For example, sulfide base potentially doesn't require as much as liquid in order to make the slurries for casting. You can pressing the materials. So there are different things that we can benefit from. But again, as we're designing, we have to have that in mind. Some of the processing that we have developed for lithium-ion batteries can apply to solid state, but not necessarily all of them. And it should be coming up with new processes where you can deconvolute. And again, we are having lithium metal that is being plated. So there is a lot of complication we are adding to our system. If we're talking about recycling in the application where you're having a sort of a module and pack, I think there's a lot of similarities. Maybe our end place will be different. The stack pressures that we're putting in are going to be different. There are some solid state that will require different foams to apply for uniformity of the lithium metal. So there is changes that are happening, and that awareness will help us know how to be ready for end of life of these cells and find out how we can recycle them in future.
Thank you very much. That was a really great dive into all the practical aspects of implementing this at the production level. We were also wondering your perspective on the need for vertical integration to ensure competitiveness in this space for solid state batteries, but also any other new battery technologies.
I think vertical integration is not an option anymore. It's definitely a necessity for the integration of new technologies. When we're talking about vertical integration, I would say one part of it is material. As I said, we are tapping into a new material portfolio, the solid state electrolyte, the anode materials. I didn't touch base equipment. That will be different. As I said, polymer base can tap into the current equipment that is designed for lithium-ion batteries. But when we're talking about sulfide base or oxide base, we'll need to look into tape casting. Well, how can we put those layers together, the stack pressure requirement, the sort of pressurized systems and lamination that has to be something that we have to adapt to. So there is a lot of equipment that we have to come up with. If you're talking about OEMs and vertical integration, I would say they don't have to own the entire value chain just because you're stretching too far, but you want to own the pieces of that value chain that you can control cost. As Stan mentioned, we need to get to that cost parity. If it is, we are trying to compete with lithium-ion batteries, solid state has to sort of compete with that. Maybe premium vehicles or premium application that high energy density and safety is mission critical can take onto that one. And they need to make sure they have enough of the minerals and the raw materials that will give them that control over the price. That will be one part that they have to be involved in. The other part is the equipment, where we need to make sure we have the right infrastructure so the material comes in and we can produce, and also the cell manufacturing. And then the other part will be really getting to that cell to module and cell to pack integration. You can have the best cell at the cell level, the highest energy density in GED and VD values, depending on if it's aviation or automotive. But as soon as you try to integrate, if you etch into that energy density by putting a lot of heavy metal to apply that stack pressure, the thermal management is going to have a different flavor. If it is polymer based, you have to heat it up. If it is oxide or sulfide based, it will have a different flavor. So all of those are the ones that you need to control: the energy density, the cycle life, the safety, the cost. Those are the part that vertical integration will play a role to have your energy security and to have that cost security that is needed, mainly in the current volatile market that we're operating within, if we cannot own and control the cost, and we're going to be cost takers. We just pay that premium price to have that technology in. So to put it in short, I think vertical integration in any application will be necessary, but we have to strategically make sure we're choosing what part of that value chain do we need to have an ownership? Do we need to have the partnership? Do we need to have those longer term agreements for the supply of the materials to know what we're assessing today, and if it's going to get into the market in 2030, we have that cost parity so we can utilize this technology in our application.
Thank you very much. That was incredibly somehow a big summary of all the perspectives inside the Battery MBA. You covered everything, and we're excited for how you bring your expertise to sort of rescuing these new technologies. So thank you. And I think now we can complete the perspective with Dr. Marek and perspectives on BESS. And I hand over to Simon.
Thank you so much, Karima. Yes, and now we already heard some great insights on where it all started and some of the new technologies, right? And now, if you look in the future, we of course also have to think about the applications of the batteries. And Stanley already mentioned, how it's evolved quite a lot since you started. But of course, one application out there is BESS, right? Stationary storage. It's something I can also say from a Battery MBA perspective. We see a lot of interest from the participants that this is, of course, a very hot application right now in a range of markets. And I would maybe like to start with you, Marek, on the technology side. So in your opinion, which innovations in batteries and BESS operation, hardware and software platform are the most promising? And maybe also kind of what are, how can BESS solution providers address these, potential safety risks, which are also due to some of failures, some of the components, and how they can really differentiate themselves to make it a, even more scalable solution as we're already seeing today?
Yeah, a lot of great questions, and there's many different aspects to this that could be tackled. But I think I'm not surprised to hear there's a lot of interest in the stationary storage space. Ultimately, it's very certain it will overtake the EVs. EVs are currently much larger as a segment, but it's a very fast growing space, because ultimately, if we need to get to a fully sustainable energy shifting system, we need a lot of storage, right, to enable that, particularly solar day to night, wind when it's in excess, and so on, right? So the longer term trajectory here is focusing more and more on longer duration applications. When I first started in storage 15 or so years ago, it was very, very high C rate, short duration systems for frequency regulation. But one of the big areas that's quite interesting at the moment is the ongoing move towards optimizing the cells in LFP for LDES, right? So larger format prismatic cells that operate at low C rates, but essentially can give you cost and material and density advantages as a result, with the trade-off that there's thermal management issues to deal with there. But because you're operating them at much lower cycles, right, once per day or even less than that if you've got a 8-hour plus battery. So that's a really interesting trend, because it's increasing the density and reducing the unit cost by being more efficient with the raw materials. And at the same time, that creates a lot of very interesting challenges. And there's a huge amount going on, not just at the cell level, but at the system level now as well, right, to optimize. That's probably where most of the gains are actually coming from these days. So we've seen one of the first problems is we've now got to a point where you can, from a volume to weight ratio, pack a lot of batteries into a container, and you run into a weight limitation for transportation and shipping. So one of the trends is actually a move back towards more modular designs. So we've started to see now blocks shipping separately, still built in the factory, but reassembled on site into something very, very compact as a footprint, because I completely agree with what Stanley was saying, that balance of system costs matter more than you think for the economics of a storage project, because it's a second order function of cost. But by shipping these units in a more smart way and actually starting to go beyond the ISO dimensions in 2D, but actually into 3D, right, and building higher systems, there's more and more energy being packed into a smaller footprint, which is helping those costs. Another big trend that I think is quite interesting, Tesla started this early with the AC block, the idea of having the string inverter, the PCS, inside the battery container. I think that's becoming very standard as the proportion of system costs, as the batteries fall and everything else becomes more dominant. So the more you can simplify the installation, the connections, all of the elements of balance of system around the projects, the more cost effective you'll be. So AC block is the first step to that. All of the largest suppliers have now moved to offering this type of design with a string inverter pre-built into the container. But what's very interesting, and it perhaps was a little bit understated, Tesla's launch of the Mega Block. It on paper doesn't look very exciting because the Mega Pack 3 is very similar to what the rest of the market has. But the idea of skidding and pre-integrating a transformer in a factory so you can deliver the whole system on site as a block, plug and play. We've yet to see how that works in practice, but that actually could be a very significant step improvement. So even if on paper the components don't look very exciting, let's say, when you put it all together, the density and the speed at which you can deploy that way is very, very interesting. So those are some of the elements, and then I'll pick one more which links to your other question about the safety risks. And it was well introduced again by Professor Whittingham with the sodium ion conversation. I fully agree from a density perspective, it matters. But one of the areas actually where we could see more of a breakthrough on sodium ion is in the stationary storage space. And that's because the polyionic chemistries, NFPP, for instance, carry a lot of potential benefits at the system level. So cell level, you'll never get to the same density as LFP. You may even need 2 cells for every one of LFP. But you can get relatively low on cost. And what you can do at the system level is quite interesting and significant, because especially in desert climates, like I'm working in the Middle East, you don't need a cooling system. You can potentially passively design your BESS, and that strips out a whole lot of cost, right? And a whole bunch of failures, because something like 90% of the battery fires that are recorded in the Clean Energy Associates database, I think EPRIs as well, are not caused by the battery cell. It's caused by an issue with, ironically, sometimes the cooling system or the fire safety system, right? Moss Landing is a good example of that, where the sprinkler system actually caused the fire. So if you can eliminate that balance of system, that's a huge advantage for safety to start with. And then at a system level, obviously, if you don't have the auxiliary power requirements and you can passively design a system, that's a huge saving in markets of extreme hot or extreme cold. So maybe I'm agreeing that you could say those are niche markets, the extreme climates, but actually a lot of our best projects are put in the sunniest places in the world, which tend to be very hot, right? So think Arizona desert, think California, think the Atacama Desert in Chile, right across the GCC region, it's the same. So I think it remains to be seen how quickly costs can come down there and whether it can head-to-head compete, because it's a very difficult incumbent to displace, but it's a lot of the same cell OEMs that are investing in the sodium ion research that are investing in LFP, and I think that's the big advantage. The same R&D might behind it, and the same production line sort of capacity that you can repurpose if it does become competitive.
Great, thank you so much, Marek, for sharing this. Really, really insightful. And you already spoke about some of the innovation and technologies and the different components and safety. Of course, now also we here in the BatteryMBA, right? There's a lot of interest how to make these projects efficient and make them work well, right? Deploy these best projects. And of course, you have gotten quite a bit of experience there with your time also with Fluence, and work on these global best projects. So maybe one thing would be like, what are the key factors which play a role to make a best project successful, right? The deployment of it. And then the second thing, which I also hear is, it feels like always you're kind of too early and too late because technology is moving, right? And there's some great questions we're going to come to later from LinkedIn. And, should you now deploy or should you wait longer and get a cheaper battery, right? Or a better system, etc. So what's like the sweet spot on this, or like how do you future-proof yourself essentially from a best perspective? Oh, sorry, you muted, Mark.
Sorry, forgot about that. I was saying it's a great question, and there isn't really a right answer to that second part of when's the right time, because you can always look backwards and say, okay, I did this at the wrong moment. But when you're looking forwards, it's pretty difficult to say. Let's say from a technology standpoint, this is an easier case than it used to be, because we used to see very aggressive cost reductions. I mean, maybe this comes back to bite me, because I've always been very bullish on how much costs will come down. And I've still been wrong most of the time. Like we haven't got Bloomberg New Energy Finance's new 2025 battery report out yet. But last year they had a 40% decline. I'm expecting it's even steeper this year. It's potentially something like 50% fall from the global average last year was $165 a kilowatt hour for a grid scale storage system. I think we're about 90 this year. So we'll see. That's my forecast. But that trend should start slowing down now. We are getting relatively close at the cell level to the raw material plus production cost plus overhead. So I can see it still declining, but maybe not a lot more. And so no longer do you have to worry about that, oh, my battery's cheaper significantly next year. At some point, we might even see a reversal if some of the policy changes in China are introduced, like the rebate on BESS and battery cell exports is introduced, or we start to see a supply and demand equalization a little bit more. So then investing earlier is the better thing. But how do you future-proof? A lot of that comes down to your technology selection, and more actually on the software and control side, right? So one of my, I think, biggest lessons from the early days, sort of doing it ourselves, because there was no one to buy a system from, right? Having to self-integrate. It's kind of like the build your own computer approach to a BESS. The software is really key to gluing it all together, and you can design something perfectly for your use case today, but in 2 years that may change, and you need to be able to change your system with it. PJM was a very good early example of that, where the signal changed and it completely changed the business case for a lot of the BESS. As new services are introduced, if you can't adapt your software and controls to them, you miss out on those revenues, or you can't optimize for them. So I think the choice of EMS is very, very important in the system, as is the design of the warranties. Too many times I see it's oversimplified, right? 1 cycle a day, and just accept that for 20 years and you get a curve. But having flexibility to bank your warranty, carry it forward if you don't use those cycles, really negotiating all the details on rest periods and average state of charge and depth of discharge, right? If you have a completely flexible warranty, you're pretty much set up for whatever comes in the future. But it's very difficult to pin down an OEM or the battery suppliers to get that very clear definition. If you know what you're asking for, there's a lot of caveats that always are sort of swept under the rug. And the last one is probably, again, selection of technology. Grid forming mode inverters, even if you don't need them today, it's probably a good idea to have a system that's capable of doing it, because in markets where inertia, VSM mode, short circuit level support are not yet needed, they will be in the future if you believe that these grids are all going to move to renewable. And ultimately, from a cost perspective, solar and wind are in most markets the cheapest form of electricity, so they will largely move towards a renewable system. So I think those are a few of the areas. I could go on, but I want to keep it brief.
Fantastic. No, thank you so much, Marek. And there's a couple of questions from online, so I want to go to them first. Of course, we have many more questions to all three of you, but there's some great questions online. And I think one was, maybe that's a bit for you, Asma and Stan, a bit about how about anode? So wait, it's Bareket who asked, how about anode-free battery for energy density and safety? Any thoughts on that?
Maybe I can answer first. There's no such thing as an anode-free battery. Every battery has an anode and a cathode. So today's batteries are built with a copper sheet as the anode. There's no lithium on it, and you plate it. So that's the standard way of doing it. And people talking about building new batteries without the lithium there. That's what we're doing today. So I'm not sure what people are really talking about. Let me emphasize, there's no such thing as an anode-free battery.
Yeah, like as a Stanman, for safety perspective, if we're talking about UN certification shipment, yes, if You do not have to form your cell before shipment, and you send it to customers. And once get there during the first cycle and the prototype protocol that you follow, you plate the lithium. Maybe for shipment, you will have that safety advantage, but you cannot sustain that lithium free or anode free. Anode free is just like as you're producing during production, you can eliminate some of that in manufacturing line safety issues. But as soon as the cell is in application, that is where safety matters. When your customers are sitting on basically on the chassis and where there's a battery that is underneath, that is where you're gonna have that lithium metals. So I wouldn't say safety will be improved. It's just gonna be where do you need to take care of it, and during the certification and shipment, what would be the advantages that we can benefit from on that anode-free systems.
Great, thank you. Rima?
Yeah, we have one more question, which maybe Mark can take as well. So it's from Zaid. Given the strong market shift from an NCA, NMC towards LFP for cost and safety reasons, do you still see a future for high nickel chemistries like NCA in EVs or grid storage, or with LFP and maybe sodium ion dominate most applications?
Well, in stationary storage, there may always be niche use cases, because if you really need a high energy dense solution, then the NCA or an NMC will give you that. But they come with a lot of trade-offs, and often the irony of it is the challenge of why you need such a high energy density is often you're in a built-up or a compressed urban area, and then you really don't want what is a relatively more dangerous chemistry to be deployed. So I think there will always be some niche use cases for the non-LFP chemistries, but at the same time, we've seen such a strong improvement in the energy density of the LFP, let's say DC block or AC block, that advantage is quite diminished at the moment. In EVs, it's less my direct expertise. I mean, if you have more constraint, part of the reason you do need the range more in an EV is because an EV is a certain size and you're not going to go drastically beyond those dimensions. So the density does matter for high-end vehicles. Where that could get interesting is, again, it's sodium ion, albeit I think it's further away for the EVs, right? So if you're looking at the layered oxides, again, good overview by Stanley on this, that it has the potential to be high density or catch up a lot on the density, but the issue is then the safety. So I don't know as well for EVs, but I think for stationary storage, LFP is the one to beat. And if there is any other sort of LDES contender, it's at the moment, from what I can see, most likely some sodium ion.
Maybe I can add a comment that I just listened to. Jeff Don gave a speech in Singapore a week ago. He raised a big red flag about LFP. LFP degrades badly above 40 degrees centigrade use. So people are putting it in two-wheelers, and he says they'll lose 30% of their capacity within 2 years. If we put them into grid storage, the grid storage is going to have to be air conditioned. So we need to be a little careful there, and it's all related to ion dissolution. So all is not good with LFP.
And I agree on that completely. So this temperature point was the one I was making earlier for why I think NFPP for sodium ion has, especially in the high temperature markets, an advantage. To take the step back, at 45 degrees, it has very similar performance to a 25-degree curve, whereas LFP falls off a cliff if you go to 45 degrees without cooling. So you're having to create a refrigerated box. I mean, and that's very standard. We have a move from air cooling to liquid cooling, and these liquid cooled systems do the job well. But in hot or very cold climates, if you're heating the system, it's a big energy drain. And again, where do we place most of our grid scale batteries? It's often in high solar markets, which tend to be quite hot. So there, I think there's a really clear case, and the two-wheeler is a good example as well, because you're not going to have an active cooling system there. And so a lot of the markets where the two-wheelers are emerging as key what do you call it, mobility vectors, it could be very interesting.
Thank you, Mark. Stan. Asma, let us know if you want to add to that?
The only thing I would say, this paradigm of one chemistry to replace the others, I think is a wrong one. Like in the context of solid state, I was like, once solid state battery comes, we're gonna replace lithium ion. No, we're not gonna do that. Lithium ion batteries had been advanced. We learned them. We have the infrastructure. They have the cost parity. We need to find out where do we need what application. If we're talking about premium vehicles, that's when you really want to work on high energy density. They can take on the higher cost. Solid state battery can play a role. If you're talking about aviation, then that is when lithium metal, every grams count. So you really want to push that for that higher energy density. You don't want to have an overkill chemistry to drive the cost up when your customer are not ready to really take that on. If you're having a mass market EV where it's going to be just for early, like daily commute, why do you need a solid state battery technology in that application? So I feel every new chemistry that comes, it should be just added to the portfolio of the product. It's going to be another solution. And you look at your application, you look at your user case, and you have to find out what would be that right chemistry and what can I do in a system and packaging level in order to make sure I have the right match. I really want to emphasize today that let's remove this think of one chemistry to replace the other. They all are complementary. We need all of them. And we're going after electrification. We need all of them. That will diversify our supply chain. That will remove the stress on one supply of the material to drive the cost up and down. And each one of them, we have to look into the user case, where they need to have that safety, that cost. If we're designing today for an application to be deployed 10 years from now, again, in the context of solid state battery, if I want to compete and I'm going to go to market 10 years from now, I need to know what lithium ion battery I need to benchmark against 10 years from now, what cost targets, what portfolio of the product I need to target. Otherwise, I'm designing a technology that 10 years from now will have a lot of competition and no one is going to be taking on that high cost just because I'm 10 or I don't know, 100 whatever per kg above what lithium ion batteries can achieve. So that will be a more holistic view that I feel we all need to develop to make sure we're having that comprehensive overview during our chemistry selection, system design, and application targets.
Great, thanks so much, Asman. I think one final question before we wrap up the public part. There was a question from Femi about today's battery industry competition. We've witnessed that some players entering the market while some others are going bankrupt. What do you think successful companies are doing right, and why are the failing companies struggling? Any learnings you have observed?
Well, we've seen that a lot in the US. You've seen it in Scandinavia, in Britain. A company can't do everything. And we keep emphasizing to our startup companies, you become an expert on the cathode, you become an expert on the anode, be an expert on the manufacturing. And my background is a battery New York prototyping facility we're building now, so we can help companies. But I think both British Volt and Northvolt failed because they said they could do everything, from making the materials, to making the cells, to making the battery packs. That expertise, you can't get that overnight. And no, the Chinese took decades to do it.
Yeah, maybe I can add an ESS perspective on this, because ironically, I think that's true for new entrants, and the challenges you're dealing and often competing with incumbents that have over time built up this vertical integration across the supply chain, and that does give the advantage over new incumbents. So if you're coming in as a new participant, you have to think a little bit cleverly. I would generally be speaking not be advising any new company to enter into the LFP space, right, unless you really have thought through that specific truth. Where there is more opportunity, again, and it's still a tricky one, because I've talked a few times about sodium ion. It's earlier in its cycle, but China is 2 years into a 5-year plan of developing the sodium ion supply chain. Yet at the same time, if you look at it, they're concerned about the supply chain for the anode, the cathode material. So, for instance, hard carbon is a lot more abundant. It's be able to produce from a lot of different resources. So geographically, the raw materials are much more diversely accessible. Same with the sodium, right? Salt, very, very widely available in the Middle East. It's a byproduct of desalination. Yet to build the midstream is very, very difficult. It's fine to have the upstream raw materials, and it's fine if you want to make your battery cells. But if you do that, and this is where Europe went, I think, wrong, is wanting to make the battery cells and feeling that that would somehow improve security of supply. But your cells are going to buy the active, the CAM, the active materials from China. So does that really help? So in terms of geographic building up of supply chains, it's to identify the right technologies that might have a chance of succeeding. Unfortunately, Europe seemed to pick green hydrogen and think it could do everything. So yeah.
Thanks for that, Mark. That's helpful. Asma, anything you want to add to it?
I would say maybe if we're talking about the new entrant being the startups, unfortunately, when we're thinking about new technologies, if it's one component of an entire cell design, whatever that is, we always think of manufacturing as a last phase. As I'm developing my technology, I am operating in silos. To be successful, I feel not only like what Marek and Stan mentioned of having that infrastructure really surrounding us and making sure we're biting the right piece that we can chew on, we also need to make sure we have that design for manufacturing in our mind. We're having a milestone base to see the progress. We need to have our customers in mind. We need to bring in OEMs. We need to bring in our customers all together. Operating in silos doesn't work anymore. We need to break those silos. Just because my cell in the lab environment works, it doesn't mean I can manufacture it tomorrow. That manufacturing discipline, industrialization discipline is different. You need to make sure that cell, you can make kilometers of electrodes with a control defect. And if, as you are scaling up, if your defect densities cannot be controlled, if you cannot have that inline metrology, if you cannot have reliability, you're just spending money where you cannot ship to customers. And as a result of it, those batteries, you're spending money. You have a technology that worked, but you didn't have that phase gate to make sure you have the right supply chain, you have the right manufacturing mindset. And I think we need to learn from OEMs. They know how important then is the quality of the suppliers that you're working with, the infrastructure that you're working with. We just blindly go and explode just because I got a huge money in my bank account, then I'm going to hire a lot of people, then I'm going to just spend and buy equipment, and I'm going to start production. And I assume what I built in the very controlled environment will scale up. That is the valley of death. And I feel bringing disciplines, manufacturing disciplines, there are no miracles. There is no material that you just work on and then that miracle material will make it. You need to make sure you're having a control over processes and you're benefiting from the different disciplines and the learning in order to make that scalability and manufacturability possible, and don't go through that valley of death of you started and then you realize, oh my God, I didn't think about all of my upstream and downstream, the infrastructure to come together in order to be successful.
Thanks so much, Asma. I think we can show one last poll here, which is kind of from the LinkedIn community, right? We asked them, what is the primary barrier inhibiting innovations for battery solution providers in the EV and BESS sectors? And it's, I think, very much aligned with what you just shared, that the scale-up challenges are truly challenging. And we have seen it also out there. I think Marek, Stanley, and Asma, you all touched on that, and I really appreciate these perspectives. Not sure if you want to add anything quick. Otherwise, I think we're going to close the public live stream because there's a lot of questions here internally in this BatteryMBA cohort. And of course, we want to make sure they get their time with you for the next 30 minutes or so. So yeah, if there's nothing quick to add here, I just want to thank you all for watching, everyone on LinkedIn and YouTube and anybody watching the recordings. If you're interested, again, joining the upcoming BatteryMBA cohort, you still have time to apply and join. If you have any questions, just send us a message. We're really happy to talk with you. And yeah, hopefully see many of you also in the upcoming cohorts, either in January or beyond. But with this, we're going to close the public part, stop the live stream, and go to our internal conversation here with this current 15th cohort. Thank you all for watching. Great. I think we're now off the live stream, so everyone can relax for a moment. And then we're going to go into internal questions. Just going to give it a moment. Everyone who's here, feel free to put on your camera. Appreciate it that it's a bit different than the normal lectures and normal conversations, but it's great to have you here. I think there's a first question from Marcus. If you want to kick us off for now.
Yes. Thank you, Simon. Yeah, first of all, thank you very much for all the presentations. Fantastic, really, really great. And especially, I think, the last comments from Asama in regards of operations, productions. I'm coming from the automotive industry, so my heart was beating when you mentioned this, and I think it's a key step, which is quite underestimated. Yeah. Nevertheless, coming back to the question, my question would be, it's basically going to all three of us. So how do you see the growth of the batteries, let's say in regards of sustainability, EV related, BESS related, within the Americas, yeah, in the next 10 to 15 years, despite the challenges of the tariffs, etc., what would be really needed to drive it up, to enhance it? Do we have a leverage, or do we depend fully on the politics right now?
I would say maybe I kind of start. Politics is having a significant impact on it. And it was heartful that when I was in Battery Show, everyone was like, so did we lose that battle? Did we just lose to China? Should we forget about it? No, we should not forget about it. I think the tariffs and the incentive, the IRA, created that urgency of bringing manufacturing in the US. We were for a long time investing on innovation, and we believe by innovation, we can get it through. And we deported that innovation to Asian market with Japanese and Korean and Chinese companies, build that infrastructure to take that innovation to, manufacturability. And yes, it took them a long time to get to this manufacturing discipline. We need to bring it in. And yes, the government support is needed. The fact that it takes us years and years of permitting in order and regulations to support us, that is hurting. We are losing that competitive advantage. And again, I feel this is the time where we should not only push for funding our innovation, but also push for making sure we are providing that infrastructure. And again, it is not about bringing gigafactories in the US. As Marek mentioned, it is also that infrastructure of the supply of the material, the fact that any minerals coming in, even if it is coming from Australia, if it's coming from South America, it goes to China for refinement and then comes here, and we pay that premium price. And if we don't start getting to that manufacturing and bringing all of us together, then we will just pay a premium price. We will lose the energy security. We will have no control over what technologies makes it at what cost, and we just will be importing, and we will pay the price of oil for the batteries to come in. And it is not, yes, right now, today, EVs are slowing down, but electrification is not about EVs only. Right. Our future, that clean energy that Stan opened up with, is requiring batteries, and batteries play a pivotal role. And as a result of it, we need to get to that infrastructure. And I think one part of it is that how academia, government, and manufacturing can come together, how we can train our workforce to have that discipline in mind, because we are having graduate students, PhDs and undergrads and all of them. But when you put them on a line to think about design for manufacturing and think about the discipline that it takes to really repeatably produce those cells, we're lacking that. And I don't want the graduate students to put back in the classes to teach them how to do manufacturing. We should put them on the line. They need to benefit from the pilot lines with the inline measurement, with all of those processes that will be taken when you're mass producing, to have that learning, faster learning. So we can take that innovation from lab to market, commercialize it in the US, and have allies, the Australian, the European, to come together, because we're having and suffering from the same problem, to be and stay competitive and have that resilient and energy security away from what Asian market can provide to us.
Great. Thank you very much.
A few comments. First, we in America have to remember USA is just part of America.
Yes.
North of the border, we have a lot of clean hydro energy. We have a lot of minerals and maybe quicker mining of those minerals than we have in the US. And I'd hope that Trump would be one that would speed up all this permitting, but it doesn't seem to be happening. I know some lithium companies in Charlotte, North Carolina want to open up some old mines. They say 10 years. This is ridiculous. There's a copper mine just south of Phoenix that could be reopened up in 2 years, but Biden said no. So to talk a little bit about Asma's comment, the building behind me, we'll be having co-op students in there on our line. The lines in there, 30 megawatt hour lines. So they're making full-size batteries, so the students will learn every step of the process. And we have smaller lines both at Binghamton and at Rochester Institute of Technology, where we have students on those lines. They get snapped up the day they graduate, they're gone. And we know companies want those, so we're trying to integrate everything. And the key thing we're trying to get the state to do is to fund a battery safety institute, because there are safety issues, but the bigger issues, a lot of cases, is NIMBY. People don't want us putting battery storage facilities next to their wind power or the solar power, or in the case they don't want them in New York City. So we have to work very hard. But anything, if we want to be competitive, we've got to have really our own supply chain. I think it takes 40 to 80 kilowatt hours of electricity to make a 1 kilowatt hour battery. A lot of that's in transportation. There are some sites in North America where we could do processing. Then they're dirty old sites like the Grand Island in New York. We could go back and do more processing there. But the challenge today is we don't really have those skills.
I was going to say the skills are really the key gap here. I completely agree with what both of the speakers said here, right? Because one is design for manufacture, and that is what China has become an extremely effective machine at. But also, to give them credit, for lack of a better term, the West thinks of itself as the sort of the intellectual leadership of R&D and pushing forward the boundaries. But actually, China has a huge R&D base as well, and if you could go to see any of these gigafactories, most of the industry, the whole city is built around the battery manufacturing, the R&D, the whole supply chain. Even for what you might not consider a tier one, a BYD or a CATL, all of the top 10, 20 names have incredible campuses. I've seen them. So that takes time to build. The US can do it, but it's a long slog. And unfortunately, probably the key thing you need is some kind of political stability and long-term support, right? If these tariffs are stable and stay, great, this will happen. But is there any certainty of that in the next, in another 3 years, that it's not going to be all change again? And no one's going to make an investment decision on mines, on production lines that pay back over 20 plus years based on a 4-year term presidency decision. And for better or worse, that's something that China has been very effective at because of the way they're set up. They can make a decision. They have 5-year plans. They stick to it, and then it follows through.
Okay, perfect. Thank you so much to all three. Appreciate it.
Perfect, thank you. I also appreciate some people have to drop off any minute, so maybe we can quickly take our group photo before we go to the next questions, which are already in the chat. So anybody who wants to be on the photo, please turn on your camera. If you don't want to be on, please turn off. Okay, there's more people. Just give it a minute. Perfect. Good to see you all. Perfect. 3 to 1. 3 to 1. Perfect. Thanks so much, everyone. Going to go to the next question. I think there's some other ones also. We're just going to go up. Great. I think there was also one on policy frameworks, which I thought was quite interesting. Julie, I think I had to already drop off. Maybe I can read it out. Do you think research should be more focused now towards recycling of lithium-ion batteries, since we already developed efficient battery systems, rather than developing more powerful battery technologies? Wondering who wants to take this on.
I don't know if it's a contrarian view, but I would say, I mean, yes, it needs to be looked at, but I wouldn't say it's, again, as high a priority as you might think. Because the opportunity is there, but again, it comes back to the last question and this ecosystem. All well and good if you can create valuable black mass from your end-of-life batteries, but if there's no refinement capability here or a new cell factory to provide those materials to at battery grade level, it's just going to be shipped back to China. So until that problem is fixed, it's a bit of it doesn't make sense to look at in isolation. That's the first point. And then the second is, again, this mistake was already made with a lot of recyclers getting very excited about end-of-life batteries. But what we're finding is the more we see them in the field, the longer they last, and there's just not the end-of-life volumes happening. We tend to find ways of preserving their life or repurposing them, or secondary markets in the case of EVs going to to other countries, and essentially anyone who is willing to accept a 50% degraded battery that still does the job to get them from A to B. So the volumes are not very predictable. And then we've seen a lot of generations of chemistry as well. So like what is a valuable raw material changes based on the generation of chemistry. And it's a big mixing problem, because if you've got all sorts of different chemistries, it's very difficult to have one recycler manage them all. And if you specialize too much, you've got too small a market share. I don't know if I'm being overly pessimistic, but I'll hand it to
I agree with your point of view. I remember when I was visiting one of the recycle, they were just taking different packs, and then they were just trying to look into, okay, if I want to go from pack to the raw material, every single pack is designed differently. They have different components. They are even not designed for recycling. And I remember at Ford, 7 years ago when I was there, they were looking into, okay, how do we look into secondary application, or do we look into recycling? I'm like, regardless, if you need to repackage, your module should be something that can be reconfigured. So you have to go after that modular design. And if you're thinking recycling, you have to think about design for manufacture, design for recycling, in order to make that cost effective and like have that line of sight. And again, breaking those cycles are important. If you're just like, I remember when there was the teardown of one of the Tesla, they're like, we cannot take it apart. The potting is so stuck. And we spend years and years in order to find out how we can, days and days to take it apart. I think those are the things as you're designing that DFX is important. What are you designing for that future? If we can benefit from, now that we spend all of that money to build into an application, once it is end of life for that application, how we can reuse them and reuse them and reuse them, then get to that recycling point, that will be beneficial. But we have to have that line of sight as we're going through production to make sure we're designing for that next step that comes in the battery life cycle.
I had a couple of comments there. We don't have the technology in the US to recycle them or to make the black mass. We saw that with Li-Cycle going bankrupt twice and some others. On the second use of batteries, NatBat and their committees basically said it's dead because no one will insure second use of batteries. And if you can't get insurance, how are you going to use it?
Yep.
Yep, that's a good point. And I think we have seen these challenges, right? And also the timing of it being so important. And I think that's a lot we talk also about, right? You have these delays you have to incorporate on the recycling. Luckily batteries get better and better, so they last longer, and then it takes more time before we can recycle them. I think there's also an interesting question about policy frameworks here from Prabha. She was focusing more, I think, on BESS, but also in general. I think Stan, you also touched on how important policy is, right, to make these things successful. Maybe from your experience, you've seen different markets. I know Marek, you also work in different places. Stan, I mean, you're a global phenomenon, so I think you're everywhere all the time, at least what I can follow on LinkedIn. Maybe what are some of the policy frameworks you think have been quite effective, right, to really nurture the local ecosystem, be it on the manufacturing, but also on the application side? Would love to hear some of your thoughts, maybe also people here in the audience thinking about what policy could be helpful in the future.
I think people in the audience need to realize the United States is 50 states. Each one has a different policy. Each one has a different attitude towards batteries. So Texas is totally against energy storage, but all the Republican ranchers are putting it in because it makes economic sense and it's good for them. So they're plowing ahead. New York has had, was it 2 years ago, 3 fires on BESS facilities. They've done a huge study of it, and there's a whole new set of regulations taking effect January the 1st. As I think Marek pointed out, it's not the cells that are the problems. Of these 3, 2 of them where the containers had holes in them, and the rainstorm, the rain got inside. The third one, by a very well-known large company, when it started going wrong, the solar power wasn't disconnected, so it kept pumping power in. And then when the firefighters got there and opened the doors, all the instructions were in an Asian language. Nothing in English, and we're not really training firefighters and first responders how to handle these fires. We have to do a better job of that, whether it's here, Europe, or elsewhere.
Yeah. So from the global perspective, there isn't, again, a single right way of doing it. And it's going to be very much in the context of the specific country or market, because there's just different philosophical views on how things should be done. Let's say the first and most important thing is actually just equitable access to markets, right? The first challenge, it's less of an issue these days with BESS, but the very first battery project I worked on over 10 years ago, installed in the Northern Irish system, needed to basically be allowed to be paid for the same services that a coal power station was being paid for. And it just wasn't written in the rules, right? So the first thing is access to provide the same services that existing thermal assets can provide, that other services can be delivered. But after that, it's then important to start paying for performance, because for a lot of the time, BESS is significantly better at providing the same services because it's faster responding, it's more accurate, it can go from 0 to full output to full charge far, far more effectively than any other type of generation asset, right? So if you pay for performance and pay a premium for it, that encourages the investment and encourages the growth. So that's just sort of free market end of the spectrum, right? Which is just having access to these services and being able to revenue jump between them. The other end of the spectrum, which has been also quite effective, is just long-term contracted revenue, right? If you want to build an asset and build it bankably with project finance from debt lenders at a low interest rate, give a 25-year contract. And batteries are getting better and better now that they can last, not just, used to be 10 years, now 15, 20, 25 is now pretty common for a utility scale system of 4 hours. And that matches with solar and wind fairly well. You can even see in some cases longer. If you can do that, you get a very low cost of finance and you basically have a guaranteed revenue, right? So it takes all of the risk out of it. Those are opposite end of the spectrum. The other two things, targets and mandates, can be useful, or they can also be problematic, because targets at least set a policy direction, but they're not generally that enforceable. But they often are very helpful because it gives an investment signal and a direction of travel of what is expected and what is needed in a given market. Mandates are, for instance, saying for every megawatt of solar you install, you need to install a 4-hour battery. So Israel, for instance, did this when it started deploying large-scale solar across the region. And China did it as well to great effect, right? There's a mandate to deploy storage with every megawatt of renewable in the different Chinese provinces. The problem with mandates is they don't tell you anything about performance. So whereas you get the performance out of these pay-for-performance assets, as you get a lot of innovation in how to optimize and use the batteries in a really clever way, the mandates, whilst they give a very simple way of making sure lots of storage gets deployed, which can help build a market, often what's not thought about is what the batteries are actually going to do. And so you end up building very cheap batteries at scale that either break or don't work properly because the actual use case wasn't thought through. So that's kind of a whirlwind tour of different mechanisms. As I say, I've seen successful examples at both ends of the spectrum. Generally, I'm a bit more of an advocate of long-term contracts because they give that stability and bring in the debt finance, which really helps accelerate deployment growth, but it has its drawbacks as well.
Great, thank you. I'm not sure, Asma, is there anything you want to add? Oh.
I think everyone touched base on everything. The only thing I would say, what Stan mentioned of US is 50 states, and each one of them have their own laws. I think the policymakers can bring focus instead of being opinion of each, state and what would be the benefits. Bringing that focus of knowing where the investment should be, where the policies can support that, and then not mandating, but creating policies with the clear roadmap that where are we today, where we want to be. And then it is not an opinion of one party versus the other. So every 3 or 4 years, you have to rethink, and that instability will be there. The policies that are going to be much more sustainable and not an opinion of if you're Democratic Party or Republican Party will give us that stability. And having that clear roadmap will make sure that there are right mandates input, there are right support, there are right talent. Again, I think in your poll, you also mentioned government support, the challenges of battery manufacturing, and the other part was the talent pool. Today, we don't have that talent pool. And with the current policies that the people who we train in the US, we cannot sustain, and we are sending them back to where the country of the origin. I think those are going to be a loss that we have to take on, and we need to enable the people who we are training to stay here. And that clear roadmap and focus will be something that will give us that cohesiveness to come together. Unfortunately, we are diverging, and we need to start converging together and work together, have that support function, and policies are going to be the backbone of pushing us in the right direction for future.
Very cool. Thanks. And I think one thing also we talk a lot about at the moment, of course, is the world of AI and how it can be, involved, and kind of how it can be a differentiator. And there's also questions here in the chat, right? Like how can certain regions be more successful? And again, AI, robotics are topics which are coming up. Based on what you are seeing, is there anything interesting you have been observing in this regard, or you're discussing in your line of work? See some nodding.
Oh,
Go ahead.
Thanks. So I'll say for the Middle East region, it's actually probably one of the topics. If you look at what Saudi Arabia and the United Arab Emirates have both said, that AI is a top priority for them, largely because the Gulf countries are seen as a bit of a neutral bridge between East and West. And here you have the fastest way to bring on power. So first we've got to step back as to why is AI important, right? But essentially because it's become a security issue. There's the productivity benefits of it, but really getting to the next model and the next level of AI is seen by the US administration and by China as a top priority. So the AI infrastructure will be built out, and that requires a huge amount of power. The fastest way to get on power is at the moment actually renewables and storage, right? You can't build anything really faster than solar and batteries and deliver power. Now, there's still the reliability elements. You may still need some engines, diesel backup, etc. But if you want to build fast, that's the best place to do it. If you have the land and if you have a good solar irradiance, because this is the challenge that a lot of the US has. It doesn't have the land, and the irradiance isn't great everywhere, which is why in the US we're seeing a lot more unmothballing. So that's the term of old generation to fire up and power hyperscale data centers. The Middle East doesn't have that problem, so it's one of the best answers I've seen to global AI demand growth and being able to address that sustainably. So there's the opportunity in terms of the storage deployment side of things there, because it's just naturally paired with solar. And that's one aspect of it. The other one will be like on the actual use of AI in making batteries smarter, more efficient, etc. But I'll leave someone else to touch on that point.
I think I'm going to add that perspective. I think one of the biggest questions that we're hearing, like AI is going to replace us. I don't think AI is going to replace human. AI and the people who are utilizing AI will replace the people who are not utilizing AI. And I think all of these infrastructure that we're building, AI is automating. And one of the things that we see in China is predictive maintenance. It is how you can utilize AI in your DOE planning for the process engineers. It's going to be an added component to your daily work. If you're a material scientist, you can benefit from AI to find out what would be that next material that you can utilize. If you're a process engineer, you can have a much more collective DOE planning to make sure you crunch in and you lower that development time. We know we are developing hardware. It's a battery. It is very CapEx intense. The hardware development, you put a lot of money, and then every iteration, every prototyping is millions of dollars that you're just learning. And as you're designing and then building and testing, that takes a lot of iteration time. You can benefit from AI. You can benefit from machine learning in order to bring that timeline in, lower that cost, and go after the right DOE as you're planning. So I would say having the fear that the robotics and AI are going to replace us is a wrong, I don't know, 10 years or 15 years from now, but immediately today in our life, we can benefit from it. China is doing it. They are getting the inline metrology. They are getting all of the infrastructure as they're manufacturing, what is coming off the line, where is the problem. So as you're doing fishbone analysis, you don't have to have your engineers going after defining every process step and reading through all of that. AI is going to give you that solution so you know what to do next. One thing we need to work on today is transfer those notes in lab books to be automated. All of the dashboards that we're creating in Excel file, how we can feed that. We need to make sure AI is getting fit with the right information, with the high quality of information, so the output that we're getting from and efficiency that it'll bring on for us will also be something that we'll utilize and stay, like, make us to be competitive. Unfortunately, I feel in that education part that we're talking about, like developing our workforce, training our workforce, that should be an element that we have to emphasize. Our education system should educate and take that fear away from the workforce and say, you're not going to be replaced. This is the tool box that will be provided to you. Tap into that. Make your work efficient, make yourself much more competitive in the market. And that will be something that I feel is going to define our roles and responsibility in a different way. It wouldn't replace our talent. AI is not there yet. Would it be there yet in 20 years? We're going to cross that line when we get there. But today, let's just benefit from utilizing it in our life and in our development process.
So we're looking at AI a little bit for our manufacturing lines. You know, what instrumentation do we need on lines to feed the AI? And how can AI predict problems before they happen and then actually identify problems on that moving line? Because in the battery gigafactory, you know, let's say the good material coming out is absolutely essential to make profit. And we understand CATL is close to 2,000 engineers working on AI and machine learning to get their production up to what, 98, 90%, 99%. We're going to have to do the same if we want to make money. So what we're going to try to do is determine what's the critical parameters in a manufacturing line that we need to know.
I'll add one more thought which occurred to me as we were discussing. Asma put it very well about the AI won't replace people full stop, right? It replaces people who don't use it. But the concern I would have, and it links to the skills gap, right, is the roles that are most effective are the junior roles, right? It's the entry level roles where you're largely helping, make notes, catalog them, sort them. These sort of things that you do when you get on the first rung of the career ladder is the one that is most easily replaceable by AI. And the challenge is you need people at the mid and senior level, right? You need still that critical thinking to be able to assess data and see, is the job well done, much like you would have a sort of mid-level manager with a junior, new recruit, new employee. But how do we get those if AI does replace those entry levels? And that's what we're starting to see a little bit in the job market. So I think I agree with a lot of the positivity around it is going to be extremely helpful, but that sort of bottom end of the job market is quite an interesting conundrum because it's the one I think at most risk. I can't remember who said it, but someone said, the jobs that aren't at risk are ironically in this sort of revolution are the blue collar jobs, right? An AI can't replace a plumber.
Yeah, at least not yet for robotics. Get more involved, but then I'm with you. I think it's a really dynamic market, and I think again it's really fascinating also in the BatteryMBA, right? We have seen over the last years to see how kind of different developments and trends really impact, right, the work we're doing. And AI is, I think, one of the later ones. I'm thinking of different chemistries and the rise of LFP and others, right, like really have shaped the work we're doing in the markets we operate in. But yeah, for today, I'm just looking at the time. Fortunately, we're running out of time. I think we covered most of the questions. If there's any other urgent question, please make sure you highlight it to us, and we can maybe still share it. There might also be some more questions on LinkedIn, so feel free to have a look there as well. But yeah, today I really want to thank our three panelists, Stan, Asma, and Marek, for sharing your insights with us. So I want to thank all of the audience, all the BatteryMBA cohort to join us and listen in and share your questions and your thoughts. I'm sure we're going to discuss some more in the office hours, as well as, of course, the case studies and the graduation this week. So it's our last week. It's always really packed, a lot to go through, but I already watched some of the fantastic case study sessions last week as well. So again, I know you're all in good shapes, and I'm really excited to see all the deliverables. But yeah, again, for today, Stan, Asma, Marek, really appreciate you spending your time with us, and we'll see you all very soon.
Thank you.
Thanks, everyone.
Best of luck with all of the students in your class, in this cohort.
So good luck, and we hope to see you active in the business.
Yes.
Stan, thanks, everyone.
Bye.
Thank you.
Thank you. Bye.